19th International Physics Olympiad, Year 1988, IPHO. Problem 1. Spectroscopy of particle velocities. Theory. Basic data. The absorption and emission of a photon is a reversible process. A good example is to be found in the excitation of an atom from the ground state to a higher energy state, and the atom's subsequent return to the ground state. In such a case, we may detect the absorption of a photon from the phenomenon of spontaneous emission or fluorescence. Some of the more modern instrumentation make use of this principle to identify atoms, and also to measure or calculate the value of the velocity in the velocity spectrum of the electron beam. In an idealized experiment, see Figure 19.1, a single charged ion travels in the opposite direction to light from a laser source with velocity v. The wavelength of light from the laser source is adjustable. An ion with velocity 0 can be excited to a higher energy state by the application of laser light having a wavelength of lambda equals 600 nanometers. If we excite a moving ion, our knowledge on Doppler's effect tells us that we need to apply laser light of a wavelength other than a value given above. There is given a velocity spectrum embracing velocity magnitude from v1 equals 0 m s to v2 equals 6000 m s. See Figure 19.1. Questions 1. Part 1. What range of wavelength of the laser beam must be used to excite ions of all velocities in the velocity spectrum given above? Part 2. A rigorous analysis of the problem calls for application of the principle from the theory of special relativity v prime equal v by square root from 1 plus v over c divided by 1 minus v over c. Determine the error when the classical formula for Doppler's effect is used to solve the problem. Question 2. Assuming the ions are accelerated by a potential u before excited by the laser beam, determine the relationship between the width of the velocity spectrum of the ion beam and the accelerating potential. Does the accelerating voltage increase or decrease the velocity spectrum width? Question 3. Each ion has the value E over m equal 4 by 10 power 6 ampere seconds over kilogram. Two energy levels corresponding to wavelength lambda 1 equals 600 nanometers and wavelength lambda 2 equals lambda 1 plus 10 power negative 3 nanometers. Show that lights of the two wavelengths used to excite ions overlap when no accelerating potential is applied. Can accelerating voltage be used to separate the two spectra of laser light used to excite ions so that they no longer overlap? If the answer is positive, calculate the minimum value of the voltage required. The 19th International Physics Olympiad, Year 1988, IPHO. Problem 1. Maxwell's wheel. Theory. Introduction. A cylindrical wheel of uniform density, having the mass m equals 0.4 kilogram, the radius r equals 0.06 meters, and the thickness d equals 0.01 meter is suspended by means of two light strings of the same length from the ceiling. Each string is wound around the axle of the wheel. Like the strings, the mass of the axle is negligible. When the wheel is turned manually, the strings are wound up until the center of mass is raised 1 meter above the floor. If the wheel is allowed to move downward vertically under the pulling force of the gravity, the strings are unwound to the full length of the strings, and the wheel reaches the lowest point. The strings then begin to wound in the opposite sense, resulting in the wheel being raised upwards. Analyze and answer the following questions, assuming that the strings are in vertical position, and the points where the strings touch the axle are directly below their respective suspending points. See Figure 19.5. Questions. Question 1. Determine the angular speed of the wheel when the center of mass of the wheel covers the vertical distance s. Question 2. Determine the kinetic energy of the linear motion of the center of mass, e, r, after the wheel travels a distance s equals 0.5 meters, and calculate the ratio between e, r, and the energy in any other form. In this problem up to this point, radius of the axle equals 0.003 meters. Question 3. Determine the tension in the string while the wheel is moving downward. Question 4. Calculate the angular speed omega prime as a function of the angle phi when the strings begin to unwind themselves in opposite sense, as depicted in Figure 19.6. Sketch a graph of variables which describe the motion in Cartesian system which suits the problem, and also the speed of the center of mass as a function of phi. Question 5. If the string can withstand a maximum tension Tm equals 10 newtons, find the maximum length of the string which may be unwound without breaking by the wheel. 19th International Physics Olympiad, 1988 year. IPH. Problem 3. Recombination of positive and negative ions in ionized gas. Theory. Introduction. A gas consists of positive ions of some element, at high temperature, and electrons. The positive ion belongs to an atom of unknown mass number Z. It is known that this ion has only one electron in the shell, orbit. Let this ion be represented by the symbol Az-1+. Constants are given that may be useful later. Question 1. Assume that the ion which has just one electron left the shell, Az-1+, is in the ground state. In the lowest energy state, the square of the average distance of the electron from the nucleus, or a square with components along x, y and z axis being delta x square, delta y square, delta z square respectively, and our 0 square equal delta x square, plus delta y square plus delta z square, and also the square of the average momentum by p0 square equal delta px square, plus delta py square, plus delta pz square, whereas delta px greater or equal Planck constant over to delta x, delta py greater or equal Planck constant over to delta y, delta pz greater or equal Planck constant over to delta z. Write inequality involving p0 square multiplied by r 0 square in a complete form. Question 2. The ion represented by AAZ-1+ may capture an additional electron, and consequently emits a photon. Write down an equation which is to be used for calculation the frequency of an emitted photon.
Question 3. Calculate the energy of the ion Az-1+ using the value of the lowest energy. The calculation should be approximated based on the following principles. 3a. The potential energy of the ion should be expressed in terms of the average value of 1 over r. That is 1 over r0, where r0 is given in the problem. 3b. In calculating the kinetic energy of the ion, use the average value of the square of the momentum given in 3.1 after being simplified by p0 square r0 square approximately equal Planck constant square. Question 4. Calculate the energy of the ion Az-2+ taken to be in the ground state, using the same principle as the calculation of the energy of Az-1+. Given the average distance of each of the two electrons in the outermost shell, same as R0 given in 3.3, denoted by R1 and R2, assume the average distance between the two electrons is given by R1 plus R2 and the average value of the square of the momentum of each electron obeys the principle of uncertainty. That is P1 square R1 square approximately equal Planck constant square and P2 square R2 square approximately equal Planck constant square. Hint: make use of the information that in the ground state R1 equal R2. Question 5. Consider in particular the ion Az-2+ is at rest in the ground state when capturing an additional electron and the captured electron is also at rest prior to the capturing. Determine the numerical value of Z if the frequency of the emitted photon accompanying electron capturing is 2.057 multiplied by 10^17 radians per second. Identify the element which gives rise to the ion.